Are you ready? Quiet up, guys. Let's get started. We've got a lot covered. So, midterm tomorrow. Please be on time. We'll hand out exams right on the hour. 50-question examination, 100-point code, multiple choice, scans-on examination. Any general questions? I gave you the ins and outs of it last time we met. For those who came to class, I think you'll do very well. So we have what? 200, I went and looked because I had to print exams. We have 286 people enrolled in the class. There's not 286 people in here. People who did not come have done themselves a big disservice. Because just studying the slides will definitely not get you a B or an A, right? It's having an understanding of what's on those slides and what they mean and how to apply them. And if you just stay home and download slides, you're not getting any of that. So people in this room already have a massive advantage over people who never came. If you study, you'll do well. But you need to apply a three-step process. It's not just memorizing the slides, it's knowing what to do with that information. And that's important. So I wish you guys the best. You have another night to study tonight. Make sure you do your computation sets again. You can do that math easy. Those are easy points. They're right off the top. That's a good 15-20% of an exam done. Simple mathematics. If you went and you gave yourself a little practice on them, it should be a cakewalk, right? Then after that, we'll get into the rest of the meat of the examination. Any general questions before I move forward today? You'll supply everything you supply the pencil. Yes? 7 to 8 in that range. Anything else? Maybe a little bit fewer. I can recall now. It's right around that 7 range. Anything else? All right, let's move forward then. So the last bit of material for the class, we'll see how much I can fit in today. I didn't realize that we got a little behind. So we'll see what we can go through. I'm not going to push the pace tremendously. What we do, we do. If not, we'll adjust. So we're talking about communities, and basically remember, two or more populations define geographic location. So characteristics of a community are very important for their definition. How can you define a community based on its characteristics? What are those characteristics? What are they? Trophic structure, okay? How many layers of energy does it take to get to you? What else?
Species diversity.
Diversity, abundance, and number count, right? What else? Dominance. What's the dominant organism there? Dominant species there, I should say. And then what's the final one?
Growth.
Yeah, it's growth form, basically, right? All right, I gave you two hypotheses. One explained why communities are put together because they're just chance assemblages that can live in the abiotic environments. What's that idea referred to as? Individualistic hypothesis. What's the idea that you're tightly interacting species all basically come through competition or fear of predation, and that's why you're together.
Interactive.
That's the interactive hypothesis. If it's this or that, it's usually what? Both, someplace in the middle, right? Okay. We talk about ecosystems. Ecosystems are dealing with the transfer and movement of energy and the cycling of nutrients. We talked about open biological systems. What does that mean? Stuff comes in and stuff goes out. So we're concerned with energy and nutrients as they come in and go out. Energy typically flows in what direction? One way. But nutrients? Cycle and spiral through a typical ecosystem. We started talking about differences in trophic levels. So what is the first trophic level that actually creates organic biomass?
Primary
producer. Primary producer is consumed by what? Primary consumer. Primary consumer is consumed by? Secondary consumer. The next level would be? Tertiary, and then a? Quaternary. Do we typically get fifth level? They're very rare. They do occur, but they are quite rare. If you were to eat like bluefin tuna, you would be a fifth level consumer. Okay? So if you go to sushi, you're all over the map in terms of your trophic level consumption. So that linear sequence of A is eaten by B, which is eaten by C, which is eaten by D. What do we refer to that as?
Food chain.
That's food chain. Is it common?
No.
Is it a lie? No. It occurs, but it's what?
Rare.
It's rare. What's by far the norm? Food webs, which are not linear, they're what? Reticulate, which means multi-linkages, right? Multi-linkages. And they're very complex. All right, I think that brings us up to speed real quickly, yes?
Yes.
So let's move forward. All right, so I want to present you some kind of symbolic way to look at energy and biomass. So we have biomass pyramids, which are referred to as ecological pyramids, and then we have energy pyramids. Which one is more symmetrical in nature? The ecological or the energy? The ecological is actually more of a symmetrical pyramid. And what that means basically is you're carrying more biomass from level to level to level, a higher percentage. Notice when you look at the energy pyramid, it's a little more asymmetrical. It tails off real quickly, right? And that's because you're losing how much energy between each level?
10%.
Well, you're losing how much though? 90% is lost, 10% is retained. The vast majority of that energy for most endothermic animals is lost as what?
Heat.
Heat. And so you can feel that right now. Put your hand to your head and you just feel that's all waste. It's all lost. So with the food that you consume for lunch, you burned up a lot of it. Most of it went to heat production and waste heat that you're losing right now to the environment. A certain proportion went to ATP production, right? But the majority of it was lost just by breaking the bonds and liberating all that heat. So when we think about biomass, biomass is a measure of dry weight. It's your carbon weight. So if I was to basically take you and desiccate you and draw all your water out, the little pile of dust that would be left, that's kind of a measure of your biomass weight. Energy, again, only about 10% of energy is transferred from one level to the next. So we have this thing called ecological efficiency, which is the trophic exchange in terms of energy from one level to the next. So trophic level transfer efficiency is a function of the production at trophic level n over the production at trophic level n minus 1. So basically we're talking about TLN divided by TLN minus 1. It's really important to know trophic level efficiencies. They tell us a lot about the world. Log on with your iClicker, please. So many of your practice problems. This is really useful. So biology has lots of applied aspects, correct? It's from my perspective, it's one of the most important facets of biology. It's its application to our general life and the well-being of the planet. And so agriculture is absolutely necessary for supporting the amount of people we have on the planet. And the amount of yield that we collect from that agriculture is critical for supporting the people that food is dependent on, right? Or that they're dependent on that food. So in this example, we have these grasshoppers. And these are basically beef-shredding grasshoppers. They're extremely destructive and they can destroy crops. And so in this particular example, we have these grasshoppers that have colonized an agricultural field and they begin to feed on the leaves of the corn. And so in this particular example, there are 150 grams per meter squared of grasshoppers, that's TL to them, and in the field of corn, and they consume 1,000 grams per meter squared of corn foliage. That's TLN minus 1. I want to know what the trophic level transfer efficiency for this grasshopper is. So this is a super easy computation, but we're going to see that it's really important. So go ahead and get together with your partner and log that in real fast for me. I'm going to learn a lot about this organism and potentially what its effects are on my crops, just by knowing how much energy is transferred between levels.
Does the weight refer to the biomass?
Yes. Okay, we're almost to our sweet spot. Put some more in there. Cut that one short. There we go. Thank you. All right, input your answers. I'm going to stop the poll. We're right where we normally get to. And let's take a look. Very nice. So in this case, there's a 93% consensus on answer C. There is a little play, though, with answer A being preferred by about 7% of the class. And that means there's simply a decimal issue there, right? So if you got answer A, please go back and make sure that you correct that decimal error, because you may see something like this on an examination. So let's take a look. Oops, sorry. C it is. And so again, it's simply a plug and play here. We got 150 divided by 1,000. That's 0.15 or 15%. So right away, I see these grasshoppers are what in terms of the average? More or less efficient? They're more efficient. So they're transferring more energy from the corn than most organisms would. What's the consequence of that energy transfer and their efficiency? What's the direct consequence of that if I'm a farmer and I know that? Should I be worried about that? I should. Why? Well, not that the crop's going down faster, but what can happen now? Basically, they're really efficient at transferring the energy from the corn into their own cells. What's the problem with that?
They're going to reproduce faster.
They're going to reproduce at a faster rate. That's exactly right. So this is important from an agricultural perspective because I don't want to see that, because that means if they're going to stay in my crop and reproduce, all of a sudden it's going to go from 1,000 grasshoppers, right, to 10 million grasshoppers. Before I know it, my entire crop will be decimated. So trophic level efficiencies are really important for agricultural systems all over the world in terms of the pests and how they're feeding in your croplands. And so biologists are directly responsible for that. Some of the work that I do deals with a little bit of trophic, subsidiary work that I do terrestrially has dealt with these kinds of issues. But in this case, the case that I work on, it's actually how efficient is a particular biocontrol at dealing with an invasive plant. Do I want it to be more or less efficient? My biocontrol agent, which is a beetle. If I want to get rid of my invasive plant, I want it to be efficient, right? I want it to decimate that plant and reproduce as fast as possible. All right, let's talk about this idea then of a top-down versus a bottom-up effect. Here's the difference. A top-down effect deals with trophic levels. The abundance of a trophic level is determined by the trophic level above, top-down. The abundance of a trophic level is determined by the trophic level below, bottom-up. That makes sense? So if you're regulated from the top, you're top-down. If you're regulated from the bottom, you're bottom-up. So when we look around the world, we see a very standard pattern. You look at terrestrial landscapes, and most of them are green. They have a lot of photosynthetic organisms and they're bright green. But when I look at certain aquatic systems, they're blue. Blue meaning there's not a lot of primary productivity going on. So when I look at the oceans, what's more productive? The tropical, pristine blue waters of the equator or the deep, thick, green-looking sludge of Alaska? The deep green-looking sludge of Alaska is by far more productive than the equatorial seas, which are completely depauperate and are basically aquatic deserts, right? The reason they're so clear and pretty blue is because there's nothing in them that's alive, right? You're looking through glass reflecting wavelengths of light that are coming through the atmosphere. When it's thick and green like that, it's because it's full of what? Algae. And there's tons of photosynthetic things going on because there's nutrients there. There's not nutrients at the equator in that same bowl. So that's why there are differences. So terrestrial environments, there's exceptions. There's lots of green aquatic systems too. But it's a big generalization. Terrestrial systems green, aquatic systems typically blue, less primary producers, a little wide. So this really deals with trophic level transfer. And so what we typically see in terrestrial systems, by far the norm is to have around 3 trophic levels and nothing more. Sometimes it'll get bigger than that, but it's usually around 3. Aquatic systems have a tendency to be more varied in the sense that they can have 3 trophic levels or 4. And that makes a major difference. So the way to look at this is we always kind of start from the top to solve the problem. So in a 3 trophic level system, I have a wolf, I have a rabbit, and I have the grass that the rabbit feeds on. So what happens if I increase the abundance of the wolf? What will happen to the abundance of the rabbit? It'll go down. What kind of effect is that? That's a top-down effect. The abundance of the rabbit is determined by the trophic level above, right? And if there are less rabbits, what does that mean for the grass? Its abundance will go up, okay? So as the wolf goes up, the rabbit goes down, and the grass goes up. That's what we should predict from a 3 trophic level system. Well, let's look at an aquatic system that has 4 trophic levels. So in this case, I have the trout. The trout loves to eat the shad. The shad loves to eat the microcrustacean. The microcrustacean loves to eat the phytoplankton. So if I increase the number of trout, what happens to the shad? It goes down. If shad go down, what happens to microcrustaceans? They go up. If I have a lot of zooplankton microcrustaceans, they're going to eat a bunch of phytoplankton. What happens to the abundance? It goes down. So look at the bottom. They're different now, right? So which one was a greener environment?
Terrestrial?
The terrestrial, because it's full of what? Grass. But over here, what happened to the phytoplankton? It all got consumed. So this water is very what? Green or blue? Blue. Is very blue. So that's an example of how you would explain why the terrestrial systems are green and some of the aquatic systems are blue. All right. You can also use this to explain where the limitation comes from in terms of abundance. whether limitations in abundance are due to resources or whether they're due to the consumers above them regulating their numbers. So your abundance as an organism set can be due to how many resources I have or things that are eating me from above, right? So let's kind of walk through this. If I am a secondary consumer, is there anything to eat me above in this case? No. So my abundance is strictly determined by what?
Food.
My food source. So I am resource limited, right? The primary consumer, in this case we look at terrestrial, it's that rabbit. Well, what is their abundance limited by? The predator above them, that was the wolf. Does it really matter how many resources are around? It's only the wolf population that's consuming me. So I'm consumer limited, I'm the rabbit. Well, since there's not a lot of rabbits around, there's going to be tons of grass, right? Do the grass care about the rabbits anymore? No, because they're not in high abundance. So their abundance is limited by what? The resource. So they're resource limited. So a 3 trophic level system is resource limited. So these are kind of word problems. They're conceptual problems. They are solved from the top to the bottom. They are coded from the bottom. What do I mean by that? I assumed that the top level went up, right? And then I worked stepwise down through the different levels. And then I code it by what the bottom actually is. So I used a series of top-down effects to tell me what was actually happening in the system and gives me whether it's resource or consumer limited. Does that make sense? So you basically would say to yourself, if I increase the top level, what does the bottom level look like? Based on the abundance of the bottom level, I can tell you whether a system's resource or consumer limited. All right, let's look at the aquatic system. Again, I have my trout, the shad, I have the zooplankton, and I have the phytoplankton. For the trout, is there any problem with predators? It is the predator, so it doesn't have to worry about anything from the top. It only has to deal with what? How much food's around, resource. But if I'm the shad, what's the problem? Tons of trout. Trout eat me, I don't have to worry about resource, I'm just worried about making surviving. So I'm consumer limited. If there's not a lot of shad, what does that mean for the microcrustaceans? I don't have to worry about consumption, I have to worry about what I can eat, which is my resource. And if there's tons of microcrustaceans, what does that mean for my prime producer, which is phytoplankton? Resources don't matter, I have to worry about who's above me because they're consuming me at high density. Make sense? So in this case, they're consumer limited. So what is the take home from this then? If you have odd number of trophic levels, you will have a resource limited trophic system. If I have an even number of trophic levels, I will have a consumer limited trophic system. So it doesn't matter if I have 5 levels, I'm still going to be what? Consumer or resource limited? I'll be resource limited. If I had 7 levels, I'll be what? Resource limited. You just do the work. Top one goes up, next one goes down, next one goes up, next one goes down. Boom, I end up with resource every single time. The same thing for the even numbered system. It can be 4, it can be 2, it can be 8, on and on and on. It will always be consumer limited. All right? So this is a nice way, theoretically, there's a math structure that works with this too, but I'm not going to give you that. Okay? I just want you to deal with the conceptual model of this. It's a model to be tested. And so I'm going to give you a test with that model because this model is predicting if I have odd, I'm what in terms of limitation? Resource. And if I'm even, I'm consumer. So let's test it. So this is a really famous study by Mary Power. It's a river ecology study that was kind of brought to overall science. She actually made a career based on it in terms of her science by coining and popularizing the term the trophic cascade. And so basically in this system it was in a river, in the Hill River in Northern California. And there were these large predatory fish which are steelhead trout. They're basically a sea-run variety of rainbow trout. So they live their life in the ocean and they run upstream to breed. And they get big, 20, 30 pounds in some cases. The grazer in the system, right, the primary consumer that she thought was this thing called a midge larva, and it's a chironomid. And what it does is it weaves the algae into these little houses. And then we have this benthic algae that you find on the rocks. And so what was her prediction? It's a 3-level system. If I raise the fish, what should happen to the grazers? They should go down, and what should happen to the algae? It should go right up. That's what the model predicts, right? Okay, well she ran this experiment by excluding fish from habitats with cages and then letting them into other areas. So it was either add the fish or get rid of the fish, right? Well, when she basically got rid of the fish, this is what happened. Is that a model match? It's not even close. She got rid of the fish, but the grazers went down, and the algae went way up. And so your question should be, why did it fail so miserably? Anybody know why?
Missing a level.
Yeah, because she screwed up, and she missed a level. That's exactly right. So she made a mistake. There was another level that she didn't anticipate. And so the level that she did not anticipate was another predatory level, which were these invertebrate predators. And so this is this cool bug. This is called Archelestes grandis. It kind of, do you guys ever see like the War of the Worlds movies where they're on the tripod moving around and they destroy everything? You ever see that thing? No? Go look at it. It's like Tom Cruise did it way back when. He made some movie. And before that, it's an H.G. Wells famous book, right? And there was other stories about it. But it's this cool kind of device where they're up on a tripod and they're kind of going down and blasting everything. It's exactly how they work. So they kind of sit real high up like this, and then see that thing underneath? It looks like a big ledge below the eyes. Kind of see going backwards? That's a really cool device. What it is prey have reactive distances. And so if the lion, you see a lion and it's a half a mile away, are you that freaked out? No, you keep your eye on it, but it's not like you're running for cover or anything yet. But if the lion is 10 feet away, are you freaking out? You should, otherwise you're lion chow, okay? So the closer you get, the predator gets to the prey, the more the prey starts to react. It's called reactive distance. Well, lots of prey in rivers and things like this can move and swim quickly. So they'll allow the predator to get really close because they think, I'll just let go and I'll be in the current and get away. Well, this thing fools them by having a protrusible mouth part that extends the distance in which they can attack. So they walk up real slow, they look at the prey's all psyched out thinking that there's no way they can reach me, and this thing uncoils, unhinges like this, and springs out, and gives them another 1/3 of body length, and then they have these claws on it, slam into the prey, and they bring the prey back. This actual device was modeled, they see it in a movie. It's a famous movie series. You guys ever seen the Alien movies? See that thing that comes flying out of the mouth, that inner jaw? That's what it looks like, okay? It's pretty cool. So anyway, this is the secondary level. So here's the thing. If you add that level, what happens? If I decrease fish, who goes up? Invertebrate predators go up because the fish aren't eating the grazers. They're actually eating that because it's a bigger food source for them. It's more nutritious. They have to eat less of them. There's better energy in return. So if the numbers basically of those go up because they're not being consumed by the fish, now these guys are able to get the grazers. There's another nuance too. This fish would like to eat the grazer, but it actually can't. And the reason it can't is that grazer takes algae and weaves it into a little house that looks like a pyramid and with a little opening in the front. And the fish can't get in there to get at it. It would love to, but it can't. However, this thing here has the thing that flies out. So they just stroll right up to the front, sight the opening, look in there, see if there's prey, and wham, in it goes, and they pull them right out of the holes. So they're real effective at it. So that drives the number of grazers down, no grazers, and the algae comes up. So that's the explanation of it. So this is not a 3-level system, it's a 4-level system. Now that it's a 4-level system, does it match the model? Perfectly, okay? So the model was actually a matcher, yes?
Wait, why does the fish go down?
Say it again?
Why does the fish go down?
That's the experiment. She drives the fish down experimentally by removing it from the system, right? Good. So this shows top-down effects. I altered the abundance of the trophic level and it cascaded through all the lower levels. Top-down effects. Let's take a look at species diversity. So we want to know, when we look at a community, how are the species numbers and their abundance determined in a particular community, and why do they change or vary over time? So species diversity is made up of 2 components. There's species richness, which is basically the number of species, and then there's species evenness, which is what is their proportion in that community. Does the species make up 90% of the community? Does it make up 5%, 10%? How many species are there, and what is their relative abundance, the proportion? Okay? So look at these 2 habitats right here. They're both tropical habitats, right? So we're going to make a little conjecture based on it. I'm going to say, in this case, the symbols represent the number of species that you find on the island. So I have how many species on each island? 3. But notice what's different on each island. The relative abundance is different, right? And this island over here is primarily all circle, which is represented in reality by what? palm trees. It's all palm trees. 90% of that community is made up of a palm tree species. 5% is something else. But this one over here, look at it. Still 3 species, but now they're broken down much more evenly. 33, 33, and 33, right? Plus to give you the 100%. So what intuitively for you is more diverse? 1 or 2?
2.
2 is intuitively more diverse, and it is, and we have metrics to actually test that. So when we test this, why is that theoretically going to be more diverse? Well, because species diversity is a function of 2 things: abundance and relative abundance and species richness, which is the number. So they start off with the same number of species, but one's more even, therefore it is more diverse. Okay? Higher species diversity for 2. All right, I'm going to introduce the very last computation that you guys will be required to know. And this is a species diversity indice. It's by far the most common. It is referred to as the Shannon-Weaver or Shannon-Weiner diversity indice. Again, an independent derivation from 2 people with similar names of all things. And it's actually generated from information technology science, which is kind of cool. But it works very well for its application to ecology. So in this particular case, it's by far the most common indice. Well, what is it saying? So H is basically the metric of species diversity. It is equal to the negative summation of P sub I log P sub I, where P sub I is the proportion of individuals contributing to the total abundance, and S is the total number of species in the community. So it's a really simple construct. I'm basically saying, how many species are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What is their proportion? 5%, 15%, 20%, and I add it all up, okay? If my H is bigger than the H from over there, this community's got more diversity than that community. That's it, pretty simple, right? So it's a very simple metric. So let's do a test here. I have community 1, I have community 2. Let's go back to our original communities. P sub I is 90% for species 1, which is the circle, 5% for the secondary and tertiary species, which are the triangle and the square. If I look at community 2, there's still 3 species, but they're evenly distributed at 33, 33, and 33. So if we do the log conversions of that, I get 0.09, 0.35, 0.35, and on the secondary community, I get 37, 37, 37. So this one's super easy. Calculate H for me. I've done all the work for you guys. You just have to add it up, right? And I want you to calculate H, and then we'll decide which one is a more diverse community. So go ahead and punch that in real fast. Notice the negative summation, okay? That's the only way you can kind of screw this one up, and forget the negative in front of the summations on it. Yes?
Is P sub I like the abundance for the individual species?
Yes. It's the proportion. Okay, put your answer in, please. Okay, we're almost at the sweet spot. A couple more. Put your answer in, please. There we go. I'm going to stop the poll right there. All right, so in this histogram, there's actually quite a lot of variability, probably more variation than I've seen all along the class so far. So there is consensus, and it's on C at about 80%. However, both A, B, and D were chosen as answers, with B being the secondary most common, at 15% of the class choosing that particular answer. And then the other ones were subsidiary, about 3% of pop. So there's definitely some numeric challenges going on with that. And it's simply because you're not looking at the negative summation. So if I have a bunch of negatives under a negative summation, I just add them up, they become positive. That's all it is. You're not doing minus and pluses as you go across, right? So in this particular case, you're just going to add them straight up. So if we were to look at it, we're looking at C as the answer there. I just add those digits up and they come out to 0.79. Do the same thing for me now for 2, and let's see if we can get more consensus without the variation in those answer sets, okay? So calculate the diversity indice for community B. Close, please put your answer in. There we go. Thank you very much. I'm going to stop the poll right there. Excellent. Okay, so in that case, we're up to 96% consensus. So everybody basically corrected any of those simple computational errors that you had. That's really nice. Let's take a look at it just to confirm that B was the answer and B it is. You simply added it up. Now the rest is easy. Which one is more diverse based on the solution to this problem? Is it A or is it B? It's definitely B, and it's simply because the value is what?
Greater.
It's greater. That's exactly right. So B is by far the most diverse community. All right. So this is a very simple question. So I'll go through it. So in this case, here's the thing. Is a natural log easy to do in your head? So will I ask for that on an examination? No, I'll supply. So I take the percentile, I calculate the natural log of that percentile, and I'll give you that value. Those are the calculations of the natural log of the percentile. Then all you have to do is what? Just add them up. Because it's a negative summation, so they just add up as positives, right? So that's it. So it's a super simple calculation. In the real world, you have to go calculate the log, and that's you just pop out your computer or your calculator and do it like that. But it takes time to do, and I won't ask you to do it. What I will do is I'll give you the percentiles, and I'll give you the logs, and then I'll expect you to solve the rest from there, which is very easy to do. Again, just use the tool form. And it's simple. Whichever one is higher, that's the more diverse community. Does that support our intuition that community B was higher?
Yes.
It does. So it's a nice match. It's a great metric to have.